On July 1st, 2025, in the darkness before dawn, a telescope in the Chilean highlands detected something that should not exist. Not in the way we understand the architecture of our cosmic neighborhood, not moving at that speed, not coming from that direction. The object was designated 3I Atlas, the third confirmed interstellar visitor to enter our solar system. Only the third time in recorded human history that we've watched something arrive from the space between the stars, carrying with it the chemistry and secrets of another stellar system entirely. It was racing toward our sun at more than 130,000 miles per hour, and every major space agency on Earth was preparing to watch. But here is what makes this story strange. Here is what keeps astronomers awake, staring at data screens, searching archives, asking questions that receive no answers. Just as 3I Atlas reached the critical moments of its approach, just as spacecraft positioned themselves for unprecedented observations, something happened. Data streams went silent. Archives showed gaps. Release schedules were pushed months into the future. And on October 1st, 2025, the United States government shut down, furloughing 83% of NASA's workforce during what should have been the most important observation window in modern astronomy. Coincidence, technical failure, or something else entirely? Tonight we're going to pull back the curtain on the observation campaign surrounding 3I Atlas. We're going to examine what was seen, what was missed, and what may have been deliberately withheld. We're going to look at the unusual chemistry that made this visitor different from anything we've studied before. We're going to explore the data gaps that appeared at precisely the wrong moments. And we're going to consider three possibilities, each more unsettling than the last. The stakes are not small. This is not just about one comet, one object, one missed opportunity. This is about transparency in science. This is about what happens when anomalies appear that don't fit our models. This is about who decides what we're allowed to see and what truths might be deemed too disruptive to share. So settle in, turn down the lights, and prepare to follow a trail of missing data, suspicious timing, and cosmic chemistry that leads us to ask the most uncomfortable question of all. What did we miss? And why weren't we allowed to see it? The story begins with a computer algorithm noticing something wrong. On July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, detected an object moving through the night sky. Atlas, the Asteroid Terrestrial Impact Last Alert System, is a NASA-funded early warning system that compares images frame by frame, searching for anything that moves. That morning, something moved. And when astronomers calculated its trajectory and velocity, they realized they were looking at something extraordinary. This object had not originated in our solar system. To understand why this matters, we need to understand what makes something interstellar. Every planet, asteroid, and comet in our solar system follows an elliptical orbit around the Sun. These orbits are bound, meaning the objects are gravitationally captured by our star, endlessly circling. But interstellar objects follow what's called a hyperbolic trajectory. They're moving so fast that the Sun's gravity cannot capture them. They pass through visitors from the deep and then they're gone forever. 3I Atlas was moving at approximately 209,000 kilometers per hour over 130,000 miles per hour. That's roughly 58 kilometers per second. This velocity, combined with the angle of approach, confirmed it immediately the third interstellar object humanity had ever detected. The first was Oumuamua in October 2017, strangely elongated and tumbling through space with non-gravitational acceleration. Harvard astronomer Avi Loeb famously suggested it might be a light sail from another civilization. Most scientists disagreed, but the debate revealed we have no framework for what interstellar visitors should look like. The second was 2I Borisov in August 2019, which behaved like a traditional comet with outgassing and a tail reassuring astronomers that interstellar objects were probably just ejected comets and asteroids. Strange but comprehensible. And then came 3I Atlas. From the moment of discovery, astronomers knew this would be special. Unlike Oumuamua already leaving when spotted 3I Atlas was inbound heading toward the Sun, that meant months of observation time. Unlike 2I Borisov, it would pass close to Mars, offering unprecedented spacecraft observation opportunities. Trajectory calculations showed 3I Atlas would reach perihelion on October 29, 2025. That gave the astronomical community 4 months to prepare to coordinate observation campaigns across agencies, universities, and research institutions worldwide. Think of it like an archaeologist discovering a sealed bottle washed ashore. Inside is a letter in an unknown language on paper from trees that don't grow on your continent using ink from foreign minerals. That bottle is a message from elsewhere carried by unmappable currents. That's what 3I Atlas represented, a message in chemistry from another star system. Space agencies mobilized. NASA coordinated with ESA. Ground observatories worldwide reserved telescope time. Hubble and the James Webb Space Telescope joined the campaign. Most intriguingly, spacecraft throughout the solar system were tasked with observing this visitor. The stage was set. Instruments were ready. The scientific community was watching. And then, as 3I Atlas drew closer, something started going wrong. But before we can understand what went wrong, we need to understand what made 3I Atlas so unusual. We need to examine the chemistry that puzzled researchers from the beginning, and why those early observations revealed something no comet should show. On August 6, 2025, the James Webb Space Telescope observed 3I Atlas with its near-infrared spectrograph. The instrument analyzed light wavelengths to determine chemical composition. What it saw confused everyone. The signature was dominated by carbon dioxide. To understand why this is strange, we need to discuss comet formation. In the early solar system, a disk of gas and dust surrounded our young sun. Moving outward, temperatures dropped. Close in, only rocky materials could condense. Beyond the snow line, water ice could form. Farther out, more volatile compounds froze. Carbon monoxide, methane, ammonia, and carbon dioxide. Most solar system comets formed where water ice dominated. When heated, water vapor is typically their primary gas, with carbon dioxide as a minor component, maybe 10–20%. But 3I Atlas was different. Its coma was dominated by carbon dioxide, suggesting formation near the CO2 ice line, a very specific temperature range. If 3I Atlas formed near this CO2 ice line, it reveals something profound about its origin. It suggests formation in conditions comparable to our outer solar system, or perhaps around a different star type, where temperature profiles created different chemistry. This pristine interstellar chemistry, locked in ice for billions of years, was being revealed as solar heat awakened the frozen volatiles. The Keck Observatory in Hawaii detected nickel and cyanide compounds in the coma. Nickel occasionally appears in comets as a trace component, but the amounts here were unusual. And when nickel appears in astronomical objects, we typically see it with iron, their companion elements forged together in stellar furnaces. But some researchers noted nickel detections without corresponding iron signatures. This could be a detection limit issue. Iron might be present, but not abundant enough to show in the wavelengths observed. But the apparent nickel without iron composition raised eyebrows, because on Earth, separating these elements requires industrial metallurgy. High nickel alloys are engineered for extreme environments, resistance to corrosion, durability in high temperatures. Natural processes in space could potentially create unusual metal ratios through differentiation in planetary bodies or unusual stellar chemistry. But it was unusual enough to note. The coma measured approximately 26,400 by 24,700 kilometers, roughly Neptune's size. Imagine a cloud of gas and dust that could swallow a planet emitted by a nucleus probably only a few kilometers across. Even in early observations, 3I Atlas didn't behave like textbook comets. The outgassing seemed more active than expected for its distance from the Sun. The coma distribution had unusual structure with hints of jets suggesting active surface vents. By late August 2025, researchers were describing it cautiously but intriguingly. Clearly, a comet clearly natural but with chemistry and behavior challenging expectations. Ground-based telescopes captured increasingly detailed images. The coma glowed greenish from diatomic carbon fluorescing in sunlight. The nucleus buried deep within was difficult to observe directly, but estimates suggested a few kilometers across. What made this compelling was the interstellar origin. Every measurement spectrum and image was a glimpse into alien world-building around a different star. Scientific papers began flowing, describing observations and offering natural explanations within comet science frameworks. Everything had explanations. Everything fit more or less into existing models, even if those models had to stretch. And then the late August images arrived. And everything got much stranger, because 3I Atlas was about to do something comets simply don't do, challenging fundamental understanding of these objects. But before we examine that anomaly, we need to understand who was watching. We need to see the vast array of instruments and spacecraft positioned to capture this moment. Because when the anomaly appeared, the question wouldn't just be what we saw. The question would be what we didn't see. And why? By late summer 2025, the coordination was remarkable. NASA, ESA, JAXA, the Chinese National Space Administration universities, private observatories, and amateur astronomers all turned their attention to this interstellar visitor. Hubble Space Telescope captured one of the first detailed images on July 21, 2025, when 3I Atlas was 277 million miles from Earth. Despite its age, Hubble remains unmatched for certain observations. The image showed 3I Atlas as a bright smudge with a developing coma, a telltale sign of comet activity. This became the baseline. Then came James Webb Space Telescope on August 6, providing the chemistry we discussed earlier. But JWST wasn't taking just one observation. Multiple viewing windows were scheduled as the object approached, building a timeline of evolving chemistry. Ground-based observatories were equally active. Keck in Hawaii collected spectroscopy. ESO's Very Large Telescope in Chile tracked the object. Smaller research telescopes contributed observations. Even amateur astronomers with sophisticated equipment captured images and submitted them to international databases. This is modern astronomy, a global network, sharing data in real time, building a complete picture from thousands of observations. But the real prizes would come from spacecraft already positioned throughout the solar system. Consider the geometry. 3I Atlas would pass relatively close to Mars in early October. And Mars hosted an extraordinary array of observational assets. ESA's ExoMars Trace Gas Orbiter, usually studying Mars's atmosphere, was perfectly positioned. It carries high-resolution cameras and spectrometers that could observe 3I Atlas from a vantage point Earth-based telescopes couldn't match. NASA's Mars Reconnaissance Orbiter carries HiRISE, capable of capturing Martian surface features as small as 30 centimeters. While designed to look down at Mars, it can point outward toward space. If HiRISE photographed 3I Atlas during Mars flyby, we might see surface features on the nucleus map. The jets determine the object's shape and rotation with unprecedented detail. The Mars encounter was scheduled for approximately October 3rd. Mark that date, remember it. But Mars wasn't the only opportunity. NASA's Psyche spacecraft, journeying to a metal-rich asteroid, carries sophisticated imaging equipment. Mission planners identified a window in early September, around September 3rd, 4th, when Psyche could observe 3I Atlas. This wasn't the primary mission, but the opportunity was there. Further out, Europa Clipper, designed to study Jupiter's moon. Europa was in cruise phase with imaging capabilities. Mission planners explored whether it might contribute late October observations. Every spacecraft is essentially a mobile observatory. If it has cameras and spectrometers, if it has line of sight, it can contribute data. This is the beauty of modern space exploration. Eyes throughout the solar system, capabilities our predecessors could only dream of observing objects from multiple angles simultaneously. The timeline was clear: July-August Hubble and JWST characterization, September Psyche observations, October Mars, flyby perihelion passage potentially Europa Clipper. Then 3I Atlas would speed outward, fading, eventually disappearing forever. One chance: interstellar objects don't orbit, they don't return. If we miss something, that data is lost forever. Every telescope and spacecraft knew their windows. Data storage was prepared, communication channels tested, analysis pipelines ready. The scientific community held its breath. Then September arrived. The first observation window opened. And something went wrong. Not catastrophic, not announced in press releases. Something subtle that would only become apparent when researchers looked for data that should have been there. The silence was deafening, and it would only grow louder. On October 1st, 2025, at 12:01 a.m. Eastern Time, the United States federal government shut down. Funding for federal agencies lapsed. Non-essential personnel were furloughed. Offices closed. Websites stopped updating. And NASA, the world's premier space agency, went dark. 83% of NASA's civil servant workforce, more than 15,000 employees, were sent home. They were told not to work, not to check email, not to access government systems. For the duration of the shutdown, they essentially ceased to exist as NASA employees. This was not unprecedented. Federal shutdowns have happened before. The longest lasted 35 days in 2018-2019, but the timing of this particular shutdown was, from a scientific perspective, catastrophically bad. 3I Atlas was approaching perihelion. It would make its closest approach to the Sun on October 29th, just 4 weeks after the shutdown began. This was the most scientifically valuable period of the entire observation campaign. This was when the object would be most active, outgassing most vigorously, potentially revealing the most about its composition and structure. And NASA's scientists, the very people who had spent months planning these observations, were locked out. Let's be clear about what continues and what stops during a government shutdown. By law, certain essential functions must continue. The International Space Station cannot be abandoned. The astronauts aboard need ground support or they die. So Mission Control in Houston remained staffed. Spacecraft already in flight continue operating. They don't care about political gridlock on Earth. Their automated systems keep functioning. The James Webb Space Telescope continued taking observations. Mars rovers continued rolling. Europa Clipper continued its cruise toward Jupiter. But here's what stopped: data processing, scientific analysis, mission planning, website updates, public communications. The flow of information from spacecraft to scientists to the public, that entire pipeline slowed to a trickle or stopped entirely. NASA's public-facing websites went into a kind of stasis. A banner appeared: "Due to the lapse in federal government funding, this website is not available. We sincerely regret this inconvenience." If you wanted to check for new images from Mars, too bad. If you wanted to see the latest JWST observations, you'd have to wait. If you were a researcher looking for raw data from the Psyche spacecraft to download and analyze, the archive was inaccessible. The human cost was immediate and cruel. NASA employees, many of whom are not highly paid despite their expertise, suddenly faced uncertainty about when their next paycheck would arrive. During previous shutdowns, furloughed workers were eventually given back pay, but there's no guarantee of that. Mortgages still need to be paid. Groceries still need to be bought. The stress was enormous. One furloughed NASA employee, speaking anonymously to reporters, described the situation as being forced to watch history pass by while you're locked outside. She was part of a team analyzing data from one of the Mars orbiters. The observations of 3I Atlas were happening. The data was being collected, but she couldn't work on it, couldn't access it, couldn't do her job. Multiply that frustration by thousands of employees, and you begin to understand the institutional trauma of a shutdown during a major scientific event. Now, there's an important timing detail we need to address because it's become a point of confusion, and in some circles, conspiracy speculation. The shutdown began October 1st, but some of the data gaps, some of the missing observations occurred earlier, in September. Before the shutdown, this matters. It means the shutdown cannot be used as a universal explanation for every missing piece of data in the 3i Atlas story. A future event cannot cause a past problem. If data from early September is missing from archives, the October shutdown is not the reason. We'll return to that point. But for now, let's focus on the shutdown's actual impact on the October observations. The Mars flyby of 3i Atlas occurred around October 3rd, just 2 days after the shutdown began. The ExoMars Trace Gas Orbiter operated by the European Space Agency continued its observations. ESA was not affected by the U.S. government shutdown, but the coordination between ESA and NASA, the data sharing, the collaborative analysis that had been planned, that was disrupted. NASA's Mars Reconnaissance Orbiter also continued operating. The spacecraft doesn't need constant human oversight. Its systems are largely automated. But the question of what data it captured and when that data would be processed and released became murky. Normally, data from Mars orbiters flows to NASA's Planetary Data System, a publicly accessible archive where researchers worldwide can download and analyze observations. During the shutdown, that flow slowed. Updates to the archive stopped. New data wasn't being uploaded on the usual schedule. This created a kind of information vacuum. Observations were happening, spacecraft were functioning, but the results weren't reaching the scientists who needed them. The shutdown lasted through most of October, finally ending in the third week of the month, just days before 3i Atlas reached perihelion on October 29th. By the time NASA employees returned to work, by the time the data pipelines restarted, the moment had partially passed. Could the observations be caught up? Could the analysis be completed retroactively? Yes, of course. Data doesn't spoil like milk, but the real-time excitement, the ability to adjust follow-up observations based on incoming results, that collaborative momentum had been broken. And here's where the shutdown created a kind of smokescreen. Because when data didn't appear on expected schedules, when archives showed gaps, when observations were delayed, the shutdown became a convenient explanation. Oh, that's because of the shutdown. Processing backlogs. Everyone's overwhelmed catching up. It provided cover, whether intentionally or not, for any other reasons data might be withheld or delayed. For researchers outside NASA, particularly international collaborators, the shutdown was frustrating in a different way. They couldn't tell what was shutdown related and what wasn't. If they requested data and received no response, was it because the person they emailed was furloughed, or because the data was being withheld for other reasons? The opacity was maddening. The European Space Agency, meanwhile, continued working without interruption. Their scientists weren't furloughed. Their websites kept updating. But as we'll discuss in the next section, ESA had its own peculiar issues with data release schedules for 3i Atlas observations. Issues that had nothing to do with American political dysfunction. Looking back at the timing, the whole situation seems almost cosmically unfortunate. Of all the months for a government shutdown, October 2025 was perhaps the worst possible choice for planetary science. It's as if the universe conspired to ensure that humanity's observation of this interstellar visitor would be compromised, fragmented, incomplete. But was it just bad luck? Just cosmic timing, or is there something more to the story? Because here's what's strange: the missing data, the gaps in archives, the delayed releases. They don't all line up with the shutdown timeline. Some occurred before. Some involved agencies that weren't affected. Some followed patterns that suggest deliberate choices rather than political happenstance. The shutdown matters. It absolutely impacted the 3i Atlas observation campaign, but it's not the whole story. It's one thread in a larger tapestry of missing information. And when you step back and look at that tapestry in its entirety, a pattern begins to emerge. A pattern of silence, of withheld observations, of data that should be public but isn't, of questions that receive no clear answers. And that pattern begins well before any politician in Washington started arguing about budget bills. Let's talk about how space mission data is supposed to work. Because understanding the normal process makes the abnormal patterns stand out in sharp relief. When a spacecraft takes an observation, whether it's a photograph, a spectrum, or a measurement, that data is stored in the spacecraft's onboard memory. Periodically, the spacecraft communicates with Earth through NASA's Deep Space Network, a collection of large radio antennas located in California, Spain, and Australia. During these communication windows, data is downloaded to ground systems. From there, the data goes through several stages. First, it's checked for integrity. Did the transmission complete correctly? Are there errors in the data? This is called level 0 processing. Then the data is converted from raw spacecraft telemetry into something scientifically usable, level 1 processing. Calibration is applied. Geometric corrections are made. The result is data that scientists can actually analyze. Finally, that processed data is uploaded to public archives. For NASA missions, this is typically the Planetary Data System. For ESA missions, it's the Planetary Science Archive. These are publicly accessible databases where any researcher anywhere in the world can download and study the observations. The timeline for this process varies by mission, but for most modern spacecraft, it's remarkably fast. Raw images from the Mars rovers often appear online within hours. JWST observations are typically public within days. The transparency is one of the great successes of the modern space age. Taxpayers fund these missions, and they get to see the results. But with 3I Atlas, something went wrong. Let's start with the Psyche spacecraft. According to NASA's own publicly posted mission schedule, Psyche was supposed to have an observation opportunity for 3I Atlas around September 3rd to 4th, 2025. The geometry was favorable. The spacecraft's cameras could be pointed at the target. It was listed as a planned observation on mission planning documents that space enthusiasts archived. But when researchers went looking for those images, they found nothing. The Psyche Raw Image Archive, which is publicly accessible and usually updated regularly as the spacecraft sends back, data showed a gap. No images from September 1st, no images from September 2nd, no images from the critical September 3rd, 4th window, no images from September 5th. The archive resumed on September 8th with routine calibration images and spacecraft engineering data, but the 3I Atlas observations absent. Completely absent. Now it's important to note that spacecraft operations don't always go as planned. Opportunities can be missed for many reasons. Perhaps the spacecraft's pointing system had a glitch. Perhaps there was a communications issue. Perhaps mission planners decided at the last minute that other priorities were more important. These things happen in the complicated ballet of interplanetary operations. But here's what's unusual. There was no explanation. NASA issued no statement about why the Psyche observations didn't happen or didn't appear in the archive. No mission blog post saying, "Unfortunately, we encountered X problem and were unable to capture the planned 3I Atlas images." No acknowledgement that the gap even existed. For researchers who had been following the mission, who had been anticipating these observations, the silence was perplexing. In the space enthusiast communities on forums and social media, people began asking questions. Where are the Psyche images of 3I Atlas? Did anyone see them? Did they exist? The questions received no answers, and the longer the silence lasted, the more peculiar it seemed. Meanwhile, the European Space Agency was having its own data drama. The ExoMars Trace Gas Orbiter successfully observed 3I Atlas during the Mars flyby in early October. ESA even acknowledged this in brief statements. But when researchers looked at ESA's Planetary Science Archive to access the data, they found something bizarre. Many of the data sets were listed with release dates in the year 2099, 74 years in the future. At first, many assumed this was a metadata error, a glitch in the database where the date field got corrupted. These things can happen in complex information systems. Default values of 99 sometimes get interpreted as years. But then something even stranger happened. The dates changed, not all of them and not all at once, but systematically. The release dates were updated to April 3, 2026. April 3, 2026. Still months in the future from when the observations were made. This wasn't a glitch. This was a deliberate embargo. Someone at ESA had made a decision this data will not be released until at least April 2026. For context, ESA's typical data release timelines for comet and asteroid observations are measured in weeks, to a couple of months, not half a year or more. The extended embargo was highly unusual. When pressed, ESA officials explained that the data required extensive calibration and validation. The observations were complex. The scientists who had proposed them deserved first opportunity to analyze and publish. These are standard justifications for data embargoes in astronomy, and they're not inherently unreasonable. But for a target that the entire world was interested in, for an interstellar object that represented a rare opportunity for the entire scientific community, the embargo felt excessive. Then there's the Mars Reconnaissance Orbiter and its high-rise camera. This spacecraft had an incredible opportunity to photograph 3I Atlas in early October. The geometry was excellent. High-rise is capable of astonishing resolution. If anyone could capture detailed surface features of the nucleus, it was high-rise. But as of months after the flyby, no high-rise images of 3I Atlas have appeared in public archives or scientific publications. The data may exist locked in processing pipelines. Or the observations may not have been attempted, or they may have failed, or they may be deliberately withheld. We don't know. And that's the problem. In the era of transparent space science, not knowing is strange. Let's contrast this with how 2I Borisov was handled. When that interstellar comet passed through in 2019, data flowed freely and quickly. Hubble images appeared online rapidly. Ground-based observations were shared within the community almost immediately. There was a sense of open collaboration of the entire astronomical world working together to understand this visitor. With 3I Atlas, the atmosphere is different. There's hesitation. There are gaps, there are embargoes, and missing data and unexplained silences. Now, could all of this be innocent? Could these be legitimate technical issues and processing delays that just happen to cluster around this one object? Of course, spacecraft are complicated, data processing is complicated, bureaucracies are slow, shutdowns happen, glitches occur, but when you map out all the gaps, when you see them laid out chronologically, a pattern emerges that's harder to dismiss as mere coincidence. September, Psyche observations missing. No explanation. Early October ExoMars data embargoed until April 2026, extended delay beyond normal. October NASA shutdown creates processing backlog and information vacuum. Late October. High-rise observations absent or unreleased. Multiple spacecraft, multiple agencies, multiple instances of data that should exist but can't be accessed, all for the same object, all during the most critical observation period. It's worth asking what would cause multiple space agencies to treat data from a single object differently than they treat data from anything else they observe. What would justify extended embargoes, unexplained gaps, and systematic delays? There are really only a few possibilities. One, massive technical failures across multiple missions simultaneously. Possible but statistically unlikely. Two, bureaucratic dysfunction amplified by the shutdown. More plausible but doesn't explain the pre-shutdown gaps or the ESA delays. Three, scientific caution. Perhaps the data is so unusual, so potentially anomalous, that institutions want to be absolutely certain before releasing it to avoid embarrassment. Or four, deliberate suppression. Perhaps something in the observations was deemed too sensitive, too controversial, too potentially disruptive to release through normal channels. We don't know which explanation is correct. We can't know without access to the data itself. And that's precisely the problem. The missing data prevents us from understanding why the data is missing. It's a circular trap. What we can say is this: the pattern of data handling for 3I Atlas does not match the pattern for other comets, asteroids, or interstellar objects we've observed. Something about this object triggered different protocols. And that difference, that deviation from the norm, is itself a piece of information. It tells us that 3I Atlas was not treated as routine. Something about it was special enough, unusual enough, concerning enough to alter how major space agencies handled the information flow. And that brings us to the question of what made it special. What did the early observations show that might have triggered these unusual responses? What anomaly appeared in the data that made 3I Atlas different from every other comet we've studied? The answer is both simple and deeply perplexing. It's an observation that challenges basic physics, an image that shows something comets aren't supposed to do, a behavior that has no easy natural explanation. And once we examine this anomaly, once we see what 3I Atlas was actually doing, the silence and the missing data start to make a different kind of sense. In late August 2025, a high-resolution image of 3I Atlas began circulating among astronomers. It would not be publicly released until October, but within the research community it caused immediate controversy. The image showed a jet, a stream of material erupting from the nucleus of the comet. But this jet was pointing in the wrong direction. It was pointing toward the sun. To understand why this is so strange, we need to review comet physics, specifically the process called sublimation and the forces that shape a comet's appearance. A comet is essentially a dirty snowball, though that's an oversimplification. The nucleus is a mixture of water, ice, frozen gases like carbon dioxide and carbon monoxide dust, and rocky material. When a comet is far from the sun, it's frozen solid, a dark, inert lump traveling through space. But as the comet approaches the sun, solar radiation heats the surface. The ices don't melt. In the vacuum of space, they sublimate, transforming directly from solid to gas. This process releases tremendous amounts of gas and dust, creating the coma, that glowing, fuzzy atmosphere around the nucleus. The sublimation isn't uniform. It happens more intensely on the sun-facing side of the nucleus. And because the nucleus is rotating, different regions heat up and cool down, creating jets, localized streams of gas and dust erupting from active areas. Now here's the critical physics: those jets carry momentum. As gas molecules escape the surface, they push against the nucleus like tiny rocket engines. This is why comets experience non-gravitational acceleration. The outgassing literally pushes them around, subtly altering their orbits. But the gas doesn't just escape randomly. It's driven by solar heating, which means it's driven outward, away from the sun. The radiation pressure from sunlight further pushes the dust particles away from the sun. This is why comet tails always point away from the sun, streaming behind the nucleus like hair blown in a wind. This is fundamental. This is Comet Physics 101. The gas and dust go outward, away from the star, always. Except 3I Atlas seemed to be violating this principle. The image clearly showed material streaming from the nucleus in a jet that appeared to be directed toward the sun. Not perpendicular, not at some angle that could be explained by rotation. Toward the sun. When astronomers first saw this, the immediate reaction was skepticism. There must be an optical illusion. There must be a projection effect where the geometry of our viewing angle makes an outward jet appear inward. There must be some kind of secondary effect, a reflection or scattering of light that creates a false impression. Researchers ran simulations. They modeled different viewing geometries. They considered every optical trick that might explain what they were seeing. And while some of those effects could contribute, they couldn't fully account for the appearance of the jet. Something genuinely unusual was happening. There's a phenomenon in some comets called an anti-tail. This occurs when dust particles, after being expelled from the nucleus, spread out along the comet's orbit. When Earth's viewing geometry aligns just right, we can see these dust trails extending in front of the comet, appearing to point forward rather than backward. Anti-tails are real, documented and understood, but the sunward jet on 3I Atlas wasn't quite the same as an anti-tail. It appeared more active, more localized, more like an actual jet of material rather than a dust trail seen from a specific angle. One hypothesis proposed that the nucleus might be venting material from a region that happened to be facing the sun at that moment, creating the appearance of a sunward jet. If the rotation axis of the nucleus was oriented in a particular way, if the active regions were in specific locations, perhaps this could create the observed effect. This is possible. Comet nuclei are irregular shapes, tumbling through space with complex rotations. Active regions can appear anywhere on the surface. If you caught the right moment at the right viewing angle, you might see something that looks unusual but is actually a normal process viewed from an atypical perspective. But here's the problem: even if the geometry could explain the appearance, it doesn't fully explain the behavior. Because other observations suggested that 3I Atlas was experiencing non-gravitational accelerations that weren't easily modeled by standard outgassing physics. When astronomers track comets, they measure their positions very precisely over time. These measurements allow them to calculate the orbit. For comets, that orbit includes not just gravity, but also the tiny pushes from outgassing. By modeling the outgassing force, you can predict where the comet will be. For 3I Atlas, the models weren't matching observations as closely as expected. The comet seemed to be accelerating in ways that required more force than typical sublimation could provide, or force directed in unexpected ways. Now, we need to be careful with this. Orbital mechanics is complicated. Non-gravitational accelerations are tricky to model because they depend on factors we can't directly observe: the rotation rate of the nucleus, the distribution of active areas, the composition of the ices, the shape of the nucleus. There's always some uncertainty. But for researchers who work with comets regularly, 3I Atlas felt different. The accelerations were larger than expected for its size and activity level. The directions didn't perfectly match what sublimation models predicted. It's as though the comet had a small rocket engine gently firing in specific directions. One researcher described the pattern as too clean, too directed. Comet outgassing is typically chaotic, averaging out to a net force but with lots of variation. This was more organized, more purposeful seeming. And then there was the halo. Several observers noted that in certain wavelengths, 3I Atlas was surrounded by a structured halo, an asymmetric cloud of material that one researcher described as space invader shaped, referencing the pixelated aliens from the 1970s arcade game. The halo had edges, geometric properties that seemed almost artificial. Could this be natural? Could plasma interactions between the comet's coma and the solar wind create such structures? Absolutely. The solar wind carries magnetic fields. Charged particles in the coma interact with those fields. You can get sheaths, bow shocks, complex plasma structures that have surprising geometry. But the combination of the sunward jet, the unusual accelerations, the structured halo, all of it together painted a picture that didn't quite fit the textbook. Here's where the speculation begins, and I want to be clear, this is speculation. This is not mainstream scientific consensus. This is a hypothesis that most astronomers do not support. But what if 3I Atlas wasn't just a comet? What if it was something else? Something actively maneuvering. Imagine a spacecraft, a probe, from another civilization using our sun for what's called an Oberth maneuver. This is a real orbital mechanics technique where you accelerate close to a massive body to gain kinetic energy. If you're traveling through interstellar space and you need to change course or boost your speed diving close to a star, and using it as a gravitational slingshot is one of the most efficient ways to do it. Such a craft would need to manage heat. It would need to vent waste. It might use solar energy for power orienting itself to capture radiation. The exhaust, the cooling systems, the orientation thrusters, all of these could create jets, plumes, and accelerations that look unusual when compared to natural comet behavior. The nickel-rich composition. Perhaps a heat-resistant hull engineered to survive close stellar approach. The structured halo. Perhaps a plasma sheath intentionally generated for radiation protection. The sunward jet. Perhaps exhaust from a thermal management system, if you approach the data with the assumption that you're looking at technology rather than geology. Many of the anomalies suddenly have explanations. But here's the challenge: extraordinary claims require extraordinary evidence. And the evidence we have, while intriguing, is not extraordinary enough to override centuries of experience with natural comets. The burden of proof for claiming artificial origin is immense, and rightly so. Most scientists examining 3I Atlas favor natural explanations, even if those explanations require unusual conditions or rare geometries. And that's appropriate. That's how science should work. You don't jump to alien probes just because a comet does something weird. But the strangeness of the observations combined with the data gaps and the institutional silence creates a nagging question. What if someone somewhere looked at this data and couldn't quite convince themselves it was natural? What if the observations were anomalous enough that they triggered additional scrutiny, internal reviews, higher-level discussions that would explain the missing data? Not because there's definitive proof of anything artificial, but because the data is ambiguous enough to be concerning, because it raises questions that space agencies might not be ready to address publicly. And that brings us to the most uncomfortable question of all: if Psyche, if HiRISE, if other spacecraft captured images of 3I Atlas during close approach, images that showed surface features or structural details that looked engineered rather than natural, what would happen to that data? Would it be released immediately, triggering a global conversation about the implications, or would it be quietly held back, reviewed by committees, classified under national security frameworks, kept from public view until someone decided the world was ready? We don't know. We can't know, but the pattern of missing observations, the systematic delays, the silence from institutions that are usually transparent, all of it suggests that something about 3I Atlas triggered protocols different from routine comet observations. And if that's true, then the sunward jet, strange as it is, might only be the beginning of the anomalies. The publicly released data might represent only what was deemed safe to share. The rest, the clearest images, the highest resolution spectra, the observations from the perfect vantage points, those might still be locked away, waiting for someone to decide what to do with them, waiting for a moment when the implications can be managed, waiting for a framework to explain what was seen, or waiting to be buried forever, classified as too sensitive, too disruptive, too reality-shattering to ever see the light of day. We may never know what was truly captured during those missing windows, but the silence itself, the gaps in the data, they speak volumes. They tell us that 3I Atlas was not routine. They tell us that something about this object was special enough to alter normal procedures, and they leave us wondering what could possibly be special enough to justify hiding it from the world. Before we venture too far into speculative territory, we need to ground ourselves in the mainstream scientific perspective. Because for every anomaly, for every strange observation, there are usually natural explanations if we're patient and thorough enough to find them. The vast majority of astronomers who have studied 3I Atlas believe it is exactly what it appears to be: a comet. An unusual comet, certainly. A comet with peculiar chemistry and unexpected behavior. But fundamentally, a natural object shaped by physics and chemistry, not by intelligence or design. Let's explore why this remains the most likely explanation despite the anomalies we've discussed. First, consider the chemistry. Yes, the carbon dioxide dominance is unusual, but unusual is not impossible. We know that different regions of protoplanetary disks have different temperature profiles, different chemical compositions, different inventories of materials. A comet forming in the outer reaches of a system around a cooler star or in a region with unusual abundances of carbon and oxygen might naturally develop a CO2-rich composition. On Earth, we're familiar with water as the dominant ice, but that's parochial. That's our local experience. In the wider cosmos, there's no reason to assume water must always dominate. Carbon dioxide, carbon monoxide, methane, ammonia, all of these can be primary components of icy bodies, depending on formation conditions. The detection of nickel, even in apparently unusual ratios, can be explained by specific types of stellar nucleosynthesis and the chemical enrichment history of whatever molecular cloud 3I Atlas formed from billions of years ago. Not every star produces elements in the same proportions. Not every planetary system inherits the same mix of heavy metals. The spectroscopy that showed nickel without obvious iron could simply be a detection limit issue. Iron might be present but not abundant enough or not in the right chemical state to produce strong emission lines in the wavelengths being observed. Absence of evidence is not evidence of absence, as the saying goes. The cyanide emissions, perfectly consistent with comet chemistry. Cyanide compounds, actually cyanoradicals, molecular fragments, are common in comets because comets contain organic molecules, carbon-bearing compounds that break apart under solar UV radiation. The presence of cyanide tells us about the organic chemistry locked inside the nucleus, the primordial molecules from the comet's birth cloud. So the chemistry, while unusual, remains within the bounds of plausible natural scenarios. It's exotic, but exotic in the way that deep-sea creatures are exotic. Strange to our experience, but still products of nature. Now let's address the sunward jet and the accelerations. This is where mainstream explanations require a bit more sophistication, but they exist. Comet nuclei are not simple spheres. They're irregular, potato-shaped, or even more complex. They rotate, often tumbling chaotically. The surface is not uniform. Some areas are covered in dust, forming a dark crust, while other areas have fresh ice exposed. When the sun heats, these active regions' jets erupt. Because the nucleus is rotating, and irregular jets can point in almost any direction at any given moment. If you happen to observe at the exact moment when an active vent on the sun-facing side of the nucleus was oriented toward the sun, you'd see material streaming sunward. It wouldn't be flowing toward the sun in the sense of moving against radiation pressure. It would simply be erupting in that direction because that's how the vent happened to be oriented at that instant. Think of it like a garden sprinkler. As it rotates, the water jet points in different directions. From certain angles, it might look like it's spraying toward the sun. But it's not violating physics, it's just geometry. The anti-tail effect can further complicate the visual appearance. When dust particles are expelled from a comet, they don't move in straight lines. They follow slightly different orbits spreading out along the comet's path. From Earth, depending on our viewing angle relative to the comet's orbit, these dust trails can appear to point in surprising directions, even forward of the nucleus. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, showed us how complex and surprising comet behavior can be. Jets erupted from unexpected locations. The rotation was complicated. The outgassing created forces that were difficult to model precisely. And that was a comet from our own solar system, one we studied intensively for years. An interstellar comet with chemistry and structure potentially quite different from our local comets might behave even more unpredictably. We shouldn't expect it to match our models perfectly when those models are based on a limited sample of solar system objects, the non-gravitational accelerations. Modeling these is notoriously difficult. You need to know the rotation period, the orientation of the rotation axis, the distribution of active areas, the rate of outgassing, the composition of the gases, all parameters that are hard to measure precisely for distant objects. Small errors in any of these parameters can lead to models that don't quite match observations. That doesn't mean the physics is wrong, it means our input data is incomplete. If we had perfect information about the nucleus of 3I Atlas, we could almost certainly construct a model that explained the accelerations, using nothing but ordinary sublimation physics. The structured halo plasma physics can create all sorts of surprising patterns. The interaction between the solar wind and a comet's coma involves magnetic fields, charged particles, shock waves, and instabilities. These systems can self-organize into geometric patterns. Nature is full of examples where simple physical processes create complex, almost architectural structures. Snowflakes, crystals, cloud formations, Saturn's hexagonal polar vortex. A space invader-shaped halo might simply be the result of a particular viewing angle of a three-dimensional plasma structure or an artifact of how the emission is distributed in different chemical species that glow at different wavelengths. In short, every single anomaly associated with 3I Atlas has plausible natural explanations. None of them individually or in combination require us to invoke technology or intelligence. This is the strength of the natural explanation. It relies on known physics. It requires no new assumptions beyond comets from other star systems might be somewhat different from ours. It's consistent with centuries of comet observations where nearly every supposedly inexplicable behavior eventually received a mundane explanation once we understood it better. Tom Statler, NASA's lead scientist for solar system small bodies, said it plainly. It looks like a comet, it acts like a comet, and it's probably a comet. The scientific community has learned through painful historical examples not to jump to extraordinary conclusions. In the 19th century, astronomers thought they saw canals on Mars, evidence of engineering by Martian civilizations. It turned out to be an optical illusion patterns imposed by the human brain on ambiguous images. In the 1960s, when pulsars were first detected, their precise regularity led some to wonder if they were alien beacons. They turned out to be neutron stars, natural objects, with physics so extreme they seemed artificial. Time and again, what initially appears inexplicable becomes explicable with more data and better understanding. This track record argues strongly for patience and conservatism. Don't invoke aliens when you haven't ruled out nature. And we haven't ruled out nature, not even close. The data we have on 3I Atlas, while intriguing, is far from complete. Much of it is ambiguous. The observations have been made from enormous distances under less than ideal conditions. We're trying to understand a kilometers-wide object millions of miles away based on photons that have traveled across space and been filtered through our atmosphere for ground-based observations, or our instruments for space-based observations. With better data, with higher resolution images, with more complete spectroscopy, many of the current mysteries would likely resolve into mundane explanations. The sunward jet might be revealed as a viewing angle effect. The accelerations might match refined models once we know the rotation state. The chemistry might fit into known paradigms once we have more complete inventories of elements and compounds. The natural explanation is not just plausible, it's the most probable scenario given our current understanding and the data we possess. To claim otherwise, to argue that 3I Atlas is anything other than a natural comet, requires far stronger evidence than we currently have. This is the scientific mainstream, and it deserves respect. It's not dogmatism or closed-mindedness. It's the application of rigorous standards of evidence and the lesson of history that nature is usually weirder and more creative than our imaginations, but still nature. However, acknowledging the strength of natural explanations doesn't mean we ignore the anomalies or dismiss the questions. Science advances by taking anomalies seriously, by investigating the edges where our models struggle, by remaining open to the possibility that our understanding is incomplete. And that's where the next level of hypothesis comes in, the unusual but still natural phenomena that might explain 3I Atlas if the conventional explanations prove insufficient. Not all natural explanations are conventional. There exists a category of phenomena that are entirely natural, requiring no intelligence or design, but which are rare enough, extreme enough, or poorly understood enough that they surprise even experienced scientists. This is the territory where 3 Atlas might genuinely be teaching us something new about comet physics without requiring us to invoke anything artificial. Let's start with plasma physics, because this is an area where our understanding is still developing, particularly for comets. When a comet approaches the sun, its coma becomes ionized. The UV radiation from the sun strips electrons from molecules, creating a plasma, a soup of charged particles. This plasma interacts with the solar wind, the stream of charged particles, flowing outward from the sun at 1,000,000 miles per hour. The interaction creates a magnetic environment around the comet. The solar wind carries its own magnetic field, and this field drapes around the coma, creating what's called a magnetic cavity. Inside this cavity, the comet's ionized gases are partially shielded from direct solar wind pressure. But this is not a stable, simple system. It's turbulent, dynamic, constantly shifting. Instabilities can develop. Plasma waves can propagate. Regions of different charge can separate, creating electric fields. Now here's where it gets interesting. These electric fields can actually accelerate charged particles, not with enormous force, but subtly over time. If the nucleus of a comet is itself charged, which it can be through photoelectric effects, where UV light ejects electrons from the surface, then electrostatic forces between the nucleus and the surrounding plasma could in principle create forces that supplement or even dominate over ordinary outgassing. This is speculative, but it's physics-based speculation. We've observed electric fields around comets. We know charging occurs. What we don't fully understand is how strong these effects can be and under what circumstances they become important for comet dynamics. If 3I Atlas passed through a particularly dense stream of solar wind, or if its composition creates unusually high levels of ionization, the plasma physics effects might be stronger than typical. This could potentially explain accelerations that don't quite match pure sublimation models. The sunward jet might even be explainable through plasma effects. If charged dust grains are accelerated by electric fields in directions that don't align with the usual radiation pressure, you could get jets that appear to point the wrong way. The particles aren't defying physics. They're responding to electromagnetic forces that we're not accounting for in simple models. This isn't mainstream, but it's within the bounds of known physics. It's just physics that's complicated and not yet fully incorporated into comet models. Another exotic but natural possibility: subsurface reservoirs and explosive outbursts. Imagine the nucleus of 3I Atlas has a crust of darker insulating material covering most of its surface. Below this crust, there are pockets of volatile ices, carbon monoxide or carbon dioxide, trapped under pressure. As the comet heats up, these subsurface ices warm and begin to sublimate, but the gas can't escape through the thick crust. Pressure builds and builds, until suddenly, catastrophically, the crust fractures and a jet of high-pressure gas explodes outward. This is not theoretical fantasy. We've observed explosive outbursts on solar system comets. Comet 17BT Holmes in 2007 suddenly brightened by a factor of 1,000,000, its coma expanding dramatically in just hours, likely due to an explosive outgassing event. Comet Schwarzmann-Wachmann 1 is famous for periodic outbursts, where its brightness increases by factors of 100 or more. These outbursts can create jets that are much stronger than ordinary sublimation, and because they're driven by subsurface structures that we can't observe, they can point in seemingly random directions. If 3I Atlas experienced such an outburst at the moment of observation, the resulting jet might look entirely anomalous, pointing sunward simply because that's where the fracture happened to occur. This explanation has the advantage of being based on documented comet behavior. It's unusual but not unprecedented, and it doesn't require new physics, just a specific set of structural conditions in the nucleus. Let's consider another exotic possibility: formation environment effects. 3IR Atlas came from another star system. What if it formed in a region that gave it properties we've simply never encountered before? What if its home system had a massive planet that gravitationally perturbed the comet, compressing its structure, creating internal stress patterns? What if it passed close to a different type of star before being ejected, receiving radiation that altered its surface chemistry in unexpected ways? Interstellar space is not empty. During its journey of potentially millions of years between star systems, 3I Atlas was bombarded by cosmic rays, high-energy particles that can penetrate deep into the nucleus and chemically alter the ices. The very top surface layers might be heavily processed, creating a radiation-damaged crust with properties unlike anything we see on comets that have spent their lives in the relatively protected environment of our solar system's outer reaches. This radiation processing could create unusual chemical species, unusual sublimation behaviors, unusual optical properties. It might give the nucleus a crust that responds to solar heating in unexpected ways, creating jets that behave differently from what our models predict. Again, this is speculative, but it's grounded in astrophysics. We know cosmic rays process materials. We know radiation chemistry can create surprising compounds. We know that interstellar comets have had histories utterly unlike solar system comets. There's also the possibility of rare extreme geometry. What if the rotation axis of 3I Atlas is oriented almost directly toward Earth? What if its rotation period is very long, keeping the same face toward the Sun for extended periods? What if the shape is extremely elongated, like Oumuamua appeared to be? Any of these geometric factors could create observational effects that make ordinary comet processes look anomalous. The sunward jet might be an ordinary jet from a pole of the nucleus that happens to be pointed in our direction. The accelerations might be ordinary but appear strange because we're viewing the comet from an unusual angle that makes it hard to interpret the directions of forces. We can't fully rule out these geometric explanations without knowing the exact shape, rotation, and orientation of 3I Atlas, and we don't have that information at the resolution needed. One more exotic natural explanation worth considering: contamination or impact history. What if during its journey through interstellar space, 3I Atlas collided with something, a small asteroid, a fragment of interstellar dust? Such a collision, even at low relative velocity, could embed foreign material into the nucleus. If that material had different properties, different chemistry, it might create localized variations in how the surface responds to solar heating. An embedded metal-rich fragment, for instance, might conduct heat differently, creating hotspots that drive asymmetric outgassing. It might even create what looks like a manufactured anomaly, a geometric pattern in the jet distribution, purely through the accident of impact and the physics of heat conduction. This is reaching, admittedly, but the universe is old, and space is vast. Unlikely things happen given enough time. All of these exotic but natural explanations share a common thread. They invoke rare conditions, unusual circumstances, or poorly understood physics, but they don't violate our fundamental understanding of how the universe works. They don't require intelligence. They don't require technology. They require only that nature, in its infinite variety, occasionally produces outliers that challenge our models. And history shows that nature does exactly that. Magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, seemed impossible until we detected them. Rogue planets, wandering through interstellar space, untethered to any star, were theoretical curiosities until surveys found them. Fast radio bursts, millisecond duration blasts of radio energy from across the universe were treated as instrument errors until they were confirmed as real astronomical phenomena. The universe is stranger than we think, and it's probably stranger than we can think. 3i Atlas might simply be the latest example of nature reminding us that our models, while good, are not complete. If the anomalies of 3i Atlas fall into this category, then the object becomes extraordinarily valuable scientifically. It's a natural laboratory for extreme comet physics. It's an opportunity to refine our models, to discover new processes to expand our understanding. And in that case, the data suppression, the missing observations become even more frustrating, because we'd be missing a chance to learn something genuinely new about how the universe works, all because institutions are either too cautious or too secretive to share what they've seen. But there's one more category of explanation we need to explore. One more hypothesis that hovers at the edge of scientific respectability, the one that most scientists don't want to discuss publicly, but that some in private conversations admit they can't completely rule out. The possibility that 3i Atlas is not natural at all. This is speculation. Let me be absolutely clear about that. What follows represents a hypothesis that most scientists do not support, and for which we do not currently have sufficient evidence. I'm presenting it not because it's likely true, but because intellectual honesty demands we consider all possibilities, even uncomfortable ones. The question is simple, even if the answer is not. Could 3i Atlas be artificial? Could it be a probe, a vessel, a constructed object from another civilization? Before you dismiss this as science fiction, consider that serious scientists have asked this question. Avi Loeb, the former chair of Harvard's astronomy department, stated publicly that he assigns a 30–40% likelihood that 3i Atlas does not have a fully natural origin. That's not a fringe conspiracy theorist. That's a tenured professor at one of the world's premier research institutions.
Loeb has been controversial for his willingness to speculate about the artificial nature of interstellar objects, particularly Oumuamua. The majority of his colleagues disagree with his conclusions, but the mere fact that such speculation exists in academic circles tells us something. The data is ambiguous enough that even experts cannot definitively rule out non-natural explanations. So let's explore this hypothesis carefully, critically, but honestly. The first question, why would anyone send a probe to another star system, particularly if that probe is just going to pass through and leave? The answer lies in a concept called the Oberth maneuver. This is a real orbital mechanics technique used by spacecraft today. The idea is that if you want to change your velocity or trajectory efficiently, you do it while moving very fast close to a massive object.
The closer to a star or planet you are when you fire your engines, the more effective your thrust becomes due to the way kinetic energy scales with velocity. If an advanced civilization wanted to explore the galaxy, they might design probes that travel from star to star, diving close to each sun to perform Oberth maneuvers using stellar gravity and energy to alter course and accelerate toward the next destination. Such a probe wouldn't orbit. It would make close passes gathering data, perhaps recharging solar power systems, then departing toward the next star. From our perspective, such probes would look exactly like interstellar objects on hyperbolic trajectories. They'd be moving too fast to be captured by the sun's gravity. They'd pass through and leave. Now, if you were designing such a probe, what would it need? First, heat management. Approaching a star closely exposes you to intense radiation and heat. You'd need materials that could withstand high temperatures. Metals like nickel are used in high-temperature applications precisely because of their thermal properties. A nickel-rich hull or coating might make sense for a sun-grazing probe. Second, you'd need attitude control. As you approach the star, you need to orient yourself correctly to maximize solar energy capture if you're recharging, or to ensure proper gravity assist trajectory. Small thrusters, perhaps, venting excess heat or using stored volatiles as propellant would create jets. Now imagine observing such a probe from Earth. You'd see a small object approaching the sun. It would be outgassing, possibly from thermal management systems or from sublimation of surface ices accumulated during the interstellar journey. It might display jets from attitude control or cooling.
It might accelerate in ways that don't perfectly match natural comet models, because the acceleration is coming from technology, not sublimation.
The sunward jet might not be a jet toward the sun, but exhaust from a system venting material for thermal management or thrust, oriented in whatever direction the probe's engineering requires. The structured halo might be a plasma sheath intentionally generated for radiation protection, the carbon dioxide chemistry. Perhaps the probe is camouflaged, designed to look like a comet with surface ices that help it blend in. Or perhaps, during its interstellar journey, it accumulated a coating of icy material from the interstellar medium, and that coating is now sublimating as it approaches our sun, making it look comet-like while hiding the artificial core beneath. This sounds like science fiction, but is it physically impossible? No. We ourselves are developing technologies that move in this direction. Solar sails that use photon pressure for propulsion. Interstellar probes like Breakthrough Starshot that could theoretically reach other stars. If we're thinking about this now, just a few thousand years into our technological development, what might a civilization 1,000,000 years older than us have achieved? The Fermi paradox asks, why, if intelligent life is common in the universe, we haven't detected any sign of it? One possible answer: we have detected signs, but we've been interpreting them as natural phenomena because we aren't looking for the right signatures. If alien probes are designed to look like asteroids or comets, if they travel through solar systems appearing as natural objects, we might never recognize them unless we examine them very, very carefully. And even then, we might mistake engineered systems for unusual natural processes. This is the unsettling implication of the artificial probe hypothesis. It suggests that our assumptions about what's natural and what's artificial might not hold when dealing with technology far more advanced than our own.
It suggests that the universe might be less empty, less silent than we think. We're just not recognizing the signals. Now let's address the massive counter-arguments to this hypothesis because they are substantial and important. First, Occam's razor. The principle that the simplest explanation is usually correct. A natural comet with unusual properties is a far simpler explanation than an alien probe. Unless we have compelling evidence for the more complex explanation, we should default to the simpler one. Second, the absence of obvious signals. If 3I Atlas is a probe, why isn't it transmitting? Why no radio signals? Why no optical beacons? SETI, the search for extraterrestrial intelligence, has been monitoring 3I Atlas, specifically looking for any artificial signals, and they've found nothing. Third, the behavior still broadly matches comets. Yes, there are anomalies, but they're not wildly outside the range of what natural processes might produce.
An artificial probe might behave in ways that are clearly non-natural perfect trajectory corrections, obviously geometric structures, materials that don't exist in nature. Fourth, the track record of similar claims. Every time someone has suggested an astronomical object might be artificial, from the Martian canals to pulsar signals to Tabby's star, the explanation has turned out to be natural. Why should this case be different? These are all valid points. They represent the mainstream scientific skepticism that keeps us from jumping to unwarranted conclusions. And they probably represent the truth. 3I Atlas is probably natural, but probably is not certainly.
And the data gaps, the missing observations, the institutional silence, they raise an uncomfortable question. What if someone looked at high-resolution images of 3I Atlas and saw something that couldn't be easily explained away? What if there are structures on that nucleus that look engineered? What if the jets, when viewed close up, have the wrong color, the wrong spectrum, the wrong geometry to be natural? Would that data be released immediately? Or would it trigger a chain of classified reviews, national security protocols, internal debates about how to handle information that might fundamentally alter human civilization's self-understanding? The artificial probe hypothesis might be unlikely, but if it were true,
The pattern of data suppression we've observed would make perfect sense. It would be exactly what we'd expect institutions scrambling to understand what they're seeing, delaying public release until they can control the narrative, perhaps ultimately deciding that the implications are too destabilizing to share. This is speculation layered on speculation. But it's important speculation because it forces us to confront the assumptions we make about what's possible in the universe and what we'd do if those assumptions proved wrong. The question is not whether 3I Atlas is an alien probe. The question is, if it were, would we even be allowed to know? And that question leads us to examine not just the comet, but ourselves, the institutions we trust to interpret the cosmos for us, the structures of authority that control information flow, the gap between what scientists see and what the public is told. Science, at its best, is a collective human endeavor. It operates on principles of transparency, reproducibility, and open debate. A researcher makes an observation, publishes the data and methods, and invites others to verify, challenge, and build upon the work. This openness is not merely idealistic. It's functional. It's how science corrects errors, how it advances understanding, how it maintains credibility. In astronomy and space science, this principle has been formalized into policies requiring public data release. NASA's official policy states that mission data should be made available to the public with minimal delay. The expectation is that within months, often weeks, observations are uploaded to archives where any researcher anywhere in the world can access them. This hasn't always been the case. In the early space age, there were long delays. Data was hoarded by small teams. Discoveries were kept secret until papers were published.
But over decades, the culture shifted toward openness, driven by both idealism and pragmatism. Transparency increases the rate of scientific discovery. It builds public trust. It justifies the enormous expense of space missions funded by taxpayers. The handling of 3I Atlas represents a troubling departure from this norm, and it's worth asking what we lose when that departure occurs. First, we lose scientific efficiency. Every day that data sits in institutional archives instead of being available to researchers is a day that discoveries are delayed. There are hundreds, perhaps thousands of scientists worldwide with expertise in comets, spectroscopy, orbital dynamics, and interstellar objects. Each has unique insights, unique analysis methods, unique questions to ask of the data. When data is withheld, all that collective intelligence is sidelined. Instead of a global community collaborating, you have a small team, however capable, working in isolation. The result is slower progress, narrower perspectives, and higher likelihood that important patterns go unnoticed. Second, we lose trust. When space agencies delay data release without clear explanation, when observation windows go missing from archives, when embargoes are extended without justification, the public and the scientific community begin to suspect motives. Is the data being withheld because it's still being processed, or because it shows something uncomfortable, or because someone has decided the public can't handle the truth? Conspiracy theories flourish in information vacuums. When official sources are silent, unofficial narratives fill the void. And once trust is eroded, it's extraordinarily difficult to rebuild. Third, we lose accountability. Public funding of space missions creates an implicit contract. Taxpayers provide billions of dollars, and in return, they gain knowledge. The discoveries belong to humanity, not to the institutions that made them. When data is withheld, this contract is violated. The public is denied the knowledge they paid for. Historically, there are legitimate reasons for data delays in certain contexts. National security can justify secrecy. Reconnaissance satellites that photograph Earth's surface to monitor potential threats are classified, and rightly so. But 3I Atlas is not a spy satellite. It's an astronomical object, a visitor from interstellar space. What national security interest is served by withholding images of a comet?
Some might argue that if 3I Atlas were genuinely anomalous, if there were credible evidence of artificial origin, then national security concerns would apply. The discovery of extraterrestrial technology would have profound implications for international relations, defense, and societal stability. In that scenario, governments might reasonably choose to classify the data until they understood the implications. But that argument creates a logical trap. If the data is withheld, we can't independently assess whether it's legitimately sensitive or whether institutions are being overly cautious. We're forced to trust that the gatekeepers are making the right call, and history suggests that institutional gatekeepers are often more concerned with protecting their institutions than with serving the public interest. Let's look at some historical parallels. In 1976, NASA's Viking landers performed experiments on Mars designed to detect microbial life. One of those experiments, the labeled release experiment, returned results that the principal investigator believed were positive for life. NASA and the broader scientific community disagreed, arguing that the results could be explained by non-biological chemistry. Decades later, the debate continues. But here's the key point: the data was released. It was made public. Researchers could and did argue about its interpretation. Transparency allowed the scientific process to function even if it didn't produce immediate consensus. Compare that to classified military reconnaissance programs. For decades, the National Reconnaissance Office operated spy satellites whose very existence was secret. When those satellites occasionally photographed scientifically interesting phenomena, the data remained classified. Researchers knew those capabilities existed, but couldn't access the observations. Some of that data has since been declassified, revealing images of archaeological sites, ice caps, volcanic eruptions, all of which would have been valuable to researchers at the time. But the delay meant that scientific questions that could have been answered in the 1970s weren't addressed until the 2000s. 30 years of lost opportunity because of classification. The question is, which model is being applied to 3I Atlas? Is it being treated as Viking data, where observations are released and debated openly, or is it being treated as reconnaissance data, classified and controlled? The pattern of missing observations and delayed releases suggests it's trending toward the latter. And that should concern us. There's also a more insidious possibility: selective release. What if institutions are choosing to release only the data that fits comfortable narratives while holding back anything genuinely anomalous? The public sees a comet that behaves strangely, but within natural bounds. The full data set, including the most troubling observations, remains classified. This wouldn't be announced as censorship. It would be framed as ongoing analysis or calibration issues or proprietary period for instrument teams. The data would be promised for future release dates, would be set and then quietly extended, and eventually the public would forget to ask. This is the danger of institutional control over information. Not that it necessarily involves malice, but that it creates opacity where there should be transparency. And in that opacity, truth can be managed, shaped, curated into forms deemed acceptable. We see this pattern in other domains. Corporate research is often withheld if it threatens profits. Medical trials with negative results are sometimes not published, creating publication bias. Government agencies classify information liberally, often for bureaucratic convenience rather than genuine security needs. Space science was supposed to be different. It was supposed to be the domain where humanity looked outward together, where discoveries were shared, where the pursuit of knowledge transcended national boundaries and institutional politics. The handling of 3I Atlas suggests that ideal is under strain. Whether from legitimate caution, bureaucratic dysfunction, or deliberate suppression, the result is the same: knowledge is being kept from those who have a right to it. And that raises a fundamental question about the future of space exploration. As our capabilities grow, as we observe more distant objects and detect more subtle phenomena, Will transparency increase or decrease? Will we move toward a model where data flows freely, or toward a model where institutions act as gatekeepers, deciding what we're allowed to know? The answer matters profoundly, because the next three-eye atlas might not be ambiguous. The next interstellar visitor might carry unambiguous signs of technology or intelligence. And when that moment comes, the question of who decides what humanity learns about its place in the cosmos will become the defining political and philosophical question of our era. In the absence of raw data, we're left with official statements, press releases, mission updates, public comments from scientists and administrators. These become our window into how space agencies are thinking about and responding to Three-Eye Atlas. So what have NASA and the European Space Agency actually said? NASA's initial announcements about Three-Eye Atlas were enthusiastic and straightforward. Press releases from July and August 2025 described the discovery as an exciting opportunity to study pristine material from another star system. Scientists from various NASA centers were quoted expressing interest in the object's chemistry and trajectory. There was clear acknowledgement that multiple NASA assets would have observation opportunities. The tone was scientific and optimistic. This was framed as a rare but ultimately routine astronomical event, an interstellar visitor that would provide valuable data about planet formation processes in other stellar systems. As September and October approached, as the critical observation windows opened, the official communications became sparse. Mission blogs for Psyche and Mars missions continued posting updates, but curiously, Three-Eye Atlas largely disappeared from these updates. The object that had been mentioned prominently in August was barely referenced in September and October. When the government shutdown began on October 1st, NASA's websites went dark, with the standard "close due to lapse in government funding" message. This was expected and applied to all of NASA's public communications, not specifically to Three-Eye Atlas content. But here's what's notable. After the shutdown ended, when NASA's websites came back online, there was no comprehensive update about Three-Eye Atlas observations. No, here's what we saw during this historic flyby press release. No summary of the data gathered by Mars orbiters. No images showcased from multiple vantage points. The silence was conspicuous precisely because it was inconsistent with how NASA usually handles interesting astronomical events. When the James Webb Space Telescope captures stunning images, they're released with fanfare. When Mars rovers find interesting rocks, we see photos within days. When asteroid missions return samples, the timeline is detailed and public. But for Three-Eye Atlas, during its closest approach, during the most scientifically valuable weeks, there was minimal official communication. ESA's approach was somewhat different. The European Space Agency did publicly acknowledge that ExoMars Trace Gas Orbiter had observed Three-Eye Atlas during the October 3rd Mars flyby. A brief statement confirmed the observations occurred and that data was being analyzed. But the data itself, as we discussed earlier, was embargoed until April 2026. When questioned about this delay, ESA officials cited standard proprietary periods for instrument teams. They explained that the researchers who had planned and executed the observations deserved first opportunity to analyze and publish the results. This is a genuine aspect of how some space missions operate. Instrument teams invest years developing cameras and spectrometers. They design observation campaigns. In return, they sometimes receive a proprietary period, months or a year, during which they have exclusive access to the data before it becomes public. However, this policy is controversial, particularly for missions funded by public agencies, and it's selectively applied. Some missions make data public immediately. Others have proprietary periods. The decision often depends on politics, institutional culture, and the specific agreements made when missions are designed. For Three-Eye Atlas, the extended embargo felt excessive to many in the community. This wasn't a targeted observation of a carefully selected exoplanet or a proprietary study of Mars geology. This was an interstellar object that the entire world was interested in. The scientific case for broad, immediate data sharing was strong. Yet ESA chose the embargo, and when pressed, officials simply reiterated policy. This pattern of, "we have data, we're analyzing it, you'll see it eventually," is consistent across agencies. It's not a refusal to release data, but rather a deferral. The message is always, wait, be patient, the process takes time. We'll tell you what we found when we're ready. For most astronomical observations, this process is tolerable. A few months' delay is annoying, but doesn't fundamentally compromise the science. Other researchers can pursue different observations, work on other projects, and catch up with the data when it's released. But for an interstellar object on a one-time pass through our solar system, delay means lost opportunity. By the time ESA's April 2026 data release arrives, 3I Atlas will be far from the Sun, much fainter, and no longer accessible to most telescopes. The observations that would build on the ESA data simply can't be made anymore. The moment has passed. This temporal aspect makes the embargo more consequential. It's not just about who gets to analyze the data first. It's about whether certain scientific questions can be addressed at all. Tom Statler, NASA's program scientist for small solar system bodies, did make one public comment that received significant attention. When asked about speculation regarding 3I Atlas potentially being artificial, Statler said simply, "It looks like a comet. It quacks like a comet. It's a comet." This was clearly intended to dampen speculation and reassure the public that nothing extraordinary was being observed. The statement emphasizes mainstream scientific consensus. 3I Atlas is a natural object behaving within expected parameters, even if those parameters include some unusual features. But this statement also raises questions. If everything is routine, if the observations are unremarkable, why the data delays? Why the missing archive entries? Why the extended embargoes? The official explanation would be that data handling issues, government shutdowns, and proprietary periods are all separate from the scientific assessment of the object. In other words, the administrative political problems surrounding data release don't reflect anything unusual about 3I Atlas itself. That's plausible. It's even likely. But it requires us to accept that a remarkable series of unfortunate events all conspired to compromise observations of one of the most interesting objects to enter the solar system in years. And humans are pattern-seeking creatures. When we see anomalies cluster, we look for common causes. The International Asteroid Warning Network, a coalition of space agencies and organizations focused on planetary defense, has been notably quiet about 3I Atlas. While interstellar objects don't pose an impact threat to Earth, they're moving too fast and on trajectories that don't intersect our planet. IAWN does coordinate observations of unusual objects. IAWN's silence might simply reflect that 3I Atlas was never considered a threat and thus fell outside their primary mandate. But it also means there's been no international coordination visible to the public, no collective statement from the global community of space agencies about what was observed. What we're left with then is a patchwork of official communications that acknowledge 3I Atlas exists, confirm that observations were made, assure us that data is being analyzed, but provide very little actual information about what was seen. For researchers and space enthusiasts accustomed to the transparency of modern astronomy, this patchwork feels incomplete. It's as though we're being told the outline of a story, but not the details. We know the chapters exist, but we can't read them. And that absence of detail, that withholding of the narrative, becomes itself a form of information. It tells us that institutions are being cautious. It tells us that whatever was observed is being treated with special care. It tells us that the easy, immediate transparency that characterizes most space science is not being applied here. Whether that's due to bureaucratic dysfunction, government shutdowns, proprietary data policies, or something more deliberate, the result is the same knowledge is being controlled, and the public is waiting for permission to know what was found in our own solar system. The story of Three-Eye Atlas does not exist in isolation. To understand what's happening with this single object, we need to zoom out and examine a broader pattern in how modern science handles anomalies, particularly in the age of automated data processing. Let's start with a technological reality. Modern astronomy produces more data than human beings can possibly examine. The Vera Rubin Observatory, which began operations in 2024, surveys the entire visible sky every few nights, generating approximately 20 terabytes of data per night. That's 20,000 gigabytes every single night. No human can look at that volume of imagery. Instead, algorithms do the first pass. Machine learning systems trained on catalogs of known objects and phenomena scan the data looking for anything interesting: supernova, asteroids, transients, variables, anomalies. This automated processing is essential. Without it, we'd drown in data. But it creates a subtle problem. The algorithms decide based on their training. What's interesting and what's noise? What gets flagged for human attention and what gets filtered out? If an observation doesn't match the patterns, the algorithm was trained to recognize it might be classified as an error. Cosmic ray hit on the detector. Satellite streak through the image. Noise. The observation goes into a rejected category and humans never see it. Now, most of the time, this filtering is exactly what we want. The vast majority of rejected observations genuinely are errors. The algorithms are good at their job, but most of the time is not all of the time. And in a universe that's under no obligation to conform to our expectations, there's always the possibility that something genuinely novel, something that doesn't match any training pattern, gets filtered out as noise. This isn't hypothetical paranoia. There are documented cases where important astronomical phenomena were initially missed because they didn't fit expected categories. Fast radio bursts. Millisecond duration pulses of radio energy from across the universe were first detected in archival data that had been sitting unnoticed for years. The original bursts had been flagged as possible terrestrial interference and ignored. Gravitational waves from colliding black holes produce tiny signals in LIGO detectors, signals that are buried in noise. Advanced filtering techniques are required to extract the signal. But that filtering is based on theoretical models of what gravitational waves should look like. If a gravitational wave source produced an unexpected waveform, it might not be recognized. The point is, our ability to discover depends on our assumptions about what's discoverable. We find what we're looking for. We sometimes miss what we're not looking for. Apply this to Three-Eye Atlas. When data from spacecraft and telescopes flows back to Earth, it passes through processing pipelines. Automated systems check for quality flag anomalies, route observations to appropriate archives. If the spectroscopy of Three-Eye Atlas shows unusual compositions, the system might flag it as anomalous and route it to manual review. If images show unexpected structures, they might be held for calibration checking. If accelerations don't match models, the data might be sent to specialists for closer examination. None of this is nefarious. It's standard procedure, but it creates a pathway where anomalous data gets diverted from the public stream and into controlled review. And once in controlled review, human judgment determines what happens next. Do the reviewers conclude the data is erroneous and discard it? Do they determine it's genuinely unusual and publish quickly? Or do they decide it's so unusual that it requires elevated review, perhaps involving administrators, perhaps triggering security protocols? We don't know. We can't know. The review processes are not public. We see only the outputs data that eventually gets released, or data that doesn't. This creates a structural problem in the age of big data and automated processing. Transparency becomes procedural rather than comprehensive. Institutions can honestly claim they're following proper protocols while simultaneously creating bottlenecks where uncomfortable data gets stuck. There's a deeper issue here about scientific culture. Science operates on consensus. Peer review replication, the gradual building of accepted knowledge through many researchers independently verifying results. This is how science self-corrects and advances.
But consensus can also be conservative. Ideas that challenge the mainstream face higher barriers. Papers proposing radical reinterpretations of data are harder to publish. Researchers who advocate for unconventional explanations risk their reputations. This conservatism is often healthy. It prevents science from being buffeted by every wild speculation. But it also means that genuine anomalies observations that don't fit existing paradigms can be systematically downplayed or dismissed. If a researcher examining 3I Atlas data sees something that doesn't match natural comet models, what are their incentives? If they write a paper suggesting the object might be artificial, they'll face intense skepticism, possibly damage their career. If they quietly suggest the data needs more study and delay publication, they stay safe. Institutions face similar pressures.
If NASA releases data suggesting an anomalous object and that interpretation turns out to be wrong, the agency faces embarrassment and loss of credibility. If they hold the data back until they're certain they protect their reputation, but compromise transparency. The structural incentives all point toward caution, delay, and conservatism, and in most cases that's appropriate. But it means that the anomalies most likely to be suppressed are exactly the ones most worth examining, the observations that don't fit that challenge, expectations that might represent genuine discoveries. We can see similar patterns in other domains. Corporate research that shows products are harmful gets suppressed. Government studies that contradict policy preferences get buried. Medical trials with negative results often go unpublished, creating a literature bias toward positive findings. The mechanisms vary, but the outcome is the same. Information that challenges authority or threatens interests is less likely to reach the public than information that supports the status quo. Space science was supposed to be different, but the 3I Atlas case suggests it's not immune to these pressures. Whether the suppression is due to scientific caution, bureaucratic incentives, or more deliberate gatekeeping, the effect is identical. We don't get to see the full picture. And this matters beyond 3I Atlas. Because if this is how anomalies are handled now, how will more dramatic discoveries be managed? If we detect unambiguous biosignatures in an exoplanet's atmosphere, will that data be released immediately? Or will it go through months or years of review while institutions debate how to frame the announcement? If a future interstellar object exhibits clearly artificial characteristics, if its behavior or structure leaves no doubt about technological origin, what happens to that data? Does it become the most important scientific discovery in history, shared immediately with all humanity? Or does it become classified, studied in secret, released only when governments decide the world is ready? The 3I Atlas case doesn't answer these questions, but it shows us the framework within which they'll be decided, and that framework appears to prioritize institutional control over public transparency. The tragedy is that this control is likely justified in the minds of those exercising it by genuine concerns, avoiding false alarms, preventing panic, ensuring accuracy, protecting national security. But those justifications can be used to suppress any discovery, no matter how important. And once we accept that institutions can withhold information for our own good, we've fundamentally altered the relationship between science and society. We're no longer collective truth seekers. We're audiences waiting to be told what we're allowed to know.
On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun. At that moment, it was approximately 65 million kilometers from our star, about 40% of the distance between Earth and the Sun. For a comet, perihelion is the climax of its journey. This is when solar heating is most intense, when outgassing is most vigorous, when activity peaks. If you want to understand what a comet is made of and how it behaves, perihelion observations are crucial. For 3I Atlas, perihelion occurred just weeks after the government shutdown began and in the midst of all the data controversies we've discussed. It should have been a moment of intense scientific focus, of coordinated observations from multiple instruments of real-time analysis and excited press releases. Instead, it was oddly quiet. The orbital mechanics of perihelion created a particular challenge. As 3I Atlas passed closest to the Sun, it also passed into solar conjunction from Earth's perspective.
This means the object moved angularly close to the Sun in our sky, making it difficult or impossible to observe from Earth-based telescopes. You can't point a telescope directly at the Sun without damaging the instruments. Solar conjunction is a routine problem in planetary science. Whenever Mars, Jupiter, or any other object passes behind or near the Sun from our perspective, we experience a communications blackout or observation gap. Mission planners know this and work around it. For 3I Atlas, the conjunction period meant that ground-based observations were limited around perihelion, but spacecraft observing from different locations in the solar system wouldn't be affected. An orbiter at Mars sees the Sun from a different angle than we do from Earth. Spacecraft on the far side of the solar system have entirely different lines of sight. This is where assets like ExoMars Mars Reconnaissance Orbiter and potentially Europa Clipper become critical. They could observe 3I Atlas during periods when Earth-based telescopes couldn't. They were the eyes that could watch the most important moments. And as we've established, the data from those spacecraft has been largely withheld or delayed. What observations were possible tell us something about how 3I Atlas responded to perihelion heating. Pre-perihelion spectroscopy showed increasing activity as expected. The coma grew brighter and larger. The outgassing intensified. These are normal comet behaviors consistent with natural processes. Some ground-based observers reported changes in the structure of the coma, variations in brightness that might indicate rotational effects or episodic outbursts. Again, not unusual for comets approaching perihelion. The surface is fracturing, pockets of volatile ices are being exposed and sublimating rapidly, causing fluctuations in activity. But the highest resolution observations, the close-up views that might have revealed surface features or resolved the structure of the jets, those remain absent from public record. After perihelion, 3I Atlas began its outbound journey. It was moving away from the Sun, now speeding toward the outer solar system and eventually interstellar space. The outgassing would gradually decrease as solar heating weakened. The coma would shrink. The object would fade. This created a ticking clock for follow-up observations. Each week that passed, 3I Atlas became harder to observe. The window for gathering data was closing, and it would never reopen. This object's hyperbolic trajectory ensures it will never return. By late November 2025, 3I Atlas had faded significantly. Ground-based telescopes could still track it, but detailed spectroscopy was becoming difficult. The signal-to-noise ratio was dropping. The most valuable observations would have been in October, during and immediately after perihelion. Those are precisely the observations complicated by the shutdown, by data delays, by the missing archive entries. Looking at the trajectory forward, 3I Atlas will continue outward, crossing the orbits of the outer planets over the coming years. Jupiter's orbit is about 5 AU from the Sun. AU, Saperchak's astronomical unit, the Earth-Sun distance. Saturn is at 10 AU. Neptune is at 30 AU. 3I Atlas will take years to reach those distances, gradually fading from view as it recedes. Eventually, perhaps in 2027 or 2028, it will become too faint for even the most powerful telescopes to detect. At that point, it will effectively disappear, a tiny dark object moving through the blackness of space, carrying whatever secrets it holds beyond the reach of human observation. The trajectory calculations show that 3I Atlas is leaving our solar system along a path that points roughly toward the constellation Telescopium. Whether that direction has any significance, whether it represents a destination or simply the random angle at which this object entered our system, we cannot know. What we do know is that we had a brief window, a few months in 2025, to study this visitor. We had spacecraft positioned throughout the solar system. We had the most advanced telescopes humanity has ever built. We had the opportunity to learn something profound about interstellar space, about the chemistry of other stellar systems, about the strange objects that wander between the stars. And much of that opportunity was squandered, not by technical failure, not by cosmic bad luck, but by institutional dysfunction, by data suppression, by the gap between what was observed and what was shared. The perihelion passage of 3I Atlas should have been a moment of triumph for astronomy, a demonstration of international cooperation and scientific capability. Instead, it became a case study in how opportunities can be lost when transparency fails. As the object fades into the distance, as it leaves the realm of human observation and returns to the cosmic dark, the questions remain. What did we miss? What was seen but not shared? What insights slipped through our fingers while we argued about budgets and debated what to release? The universe will send us other visitors. Perhaps sooner than we think. New detection systems like the Vera Rubin Observatory are coming online, systems that will spot interstellar objects years before they reach the inner solar system, giving us more time to prepare, more opportunity to study them.
When the next visitor arrives, will we do better? Will the lessons of 3I Atlas lead to reforms in data handling, to commitments to transparency, to institutional cultures that prioritize science over caution? Or will we repeat the same patterns? Will we see the same data gaps, the same delays, the same silence when answers are most needed? The answer depends on whether we demand better, whether the scientific community and the public insist that space science remain open, collaborative, and transparent, whether we accept institutional gatekeeping or push back against it. 3I Atlas, whether natural or something more, has already taught us something important. It's shown us that our systems for handling cosmic discoveries are not as robust as we believed, that transparency is fragile, that when truly unusual data emerges, the impulse to control can override the commitment to share. That lesson, uncomfortable as it is, might be the most valuable thing this interstellar visitor leaves behind. Step back from the specifics of 3I Atlas for a moment. Look at the bigger picture. What does the existence of interstellar objects tell us about the universe and our place in it? First, it tells us that space between the stars is not empty. For much of human history, we imagined the void between stellar systems as absolute emptiness, a vacuum so perfect that nothing could exist there. We were wrong. The galaxy is filled with wanderers, asteroids and comets ejected from their birth systems by gravitational interactions with planets, orphaned worlds, rogue planets flung into darkness, perhaps even the remnants of destroyed star systems, debris from stellar collisions or supernovae. And now we must consider the possibility of artificial objects, probes sent by civilizations to explore the cosmic neighborhood. Recent estimates based on the detection rate of interstellar objects suggest that one might pass through the inner solar system every few years. We've confirmed only 3 so far: Oumuamua, 2I Borisov, and 3I Atlas, but that's because our detection capabilities are limited. Most interstellar objects probably pass through unnoticed, too small or too dark to trigger our surveys. The Vera Rubin Observatory, with its enormous field of view and rapid surveying capability, is expected to detect dozens of interstellar objects per year once it's fully operational. Within a decade, we might have a catalog of hundreds of these visitors, each carrying information about its origin system. This transforms our understanding of planetary science. We no longer need to travel to other stars to study their planets and comets.
The stars send samples to us. Each interstellar object is a free sample of alien world building delivered to our instruments. The chemistry alone is revolutionary. By analyzing the isotopic ratios in interstellar objects, we can infer properties of their birth stars. Different stellar types produce different abundances of elements. A comet formed around an M-dwarf star might have different chemistry than one formed around a G-type star like our Sun. We can study how planetary systems form under various conditions. We can test our theories of planet formation against data from systems we'll never directly observe. We can ask, is our solar system typical or unusual? Are the patterns we see here universal or local? For astrobiology, the implications are profound. If comets from other systems carry organic molecules, if they contain the building blocks of life, it strengthens the case that life's chemistry might be common throughout the galaxy. Water, carbon dioxide, organic compounds. If these appear consistently in interstellar objects, it suggests they're universal features of planet formation, not cosmic accidents specific to Earth. And if life is based on universal chemistry, then life itself might be common. Not guaranteed, but plausible. The universe might be far more alive than we've dared to imagine, but there's a darker implication as well. If interstellar objects pass through regularly, if the space between stars is filled with debris, then Earth's environment is not as isolated as we once believed. We exist in a cosmic shooting gallery. Most interstellar objects pass harmlessly by. Their trajectories don't intersect Earth's orbit. They're no threat, but not all trajectories are safe. Eventually, statistically, an interstellar object will be on a collision course with Earth. And when that happens, our detection systems and planetary defense strategies will face their ultimate test. An interstellar impactor would be far more dangerous than a typical asteroid or comet. It would approach at higher velocity, meaning more kinetic energy, more destructive potential. It would be harder to deflect because it's moving so fast. And because interstellar objects spend most of their time in deep space, they're cold, dark, and difficult to detect until they're already close. This isn't fear-mongering. This is probability. The universe is old. Earth has been hit by asteroids and comets throughout its history, events that reshaped the planet's biology and geology. The Chicxulub impact 66 million years ago, which contributed to the extinction of the dinosaurs, was almost certainly a solar system object. But there's no reason an interstellar object couldn't do the same. Planetary defense programs like NASA's DART mission and ESA's Hera mission are preparing us for this scenario. We're learning how to track potential threats, how to model their trajectories, how to deflect them if necessary. The fact that Hera is being developed now in 2025-2026, while we're still processing the 3I Atlas encounter, is not coincidental. These programs are justified by the very real threat from solar system asteroids.
But interstellar objects add a new dimension to the challenge. We need detection systems that can spot dark, fast-moving objects earlier. We need deflection strategies that work against higher velocity targets. We need international protocols for responding to threats that cross national boundaries by definition. The existence of interstellar visitors is forcing us to mature as a spacefaring civilization. We can no longer think of the solar system as a closed system. We're part of a galactic ecosystem. Objects flow in and out, and we need to understand that flow to ensure our survival. There's also a philosophical dimension. The confirmation that interstellar objects exist, that they visit regularly, changes how we think about humanity's isolation. For thousands of years, we've been alone on Earth, looking up at stars that seemed unreachably distant. The space between was a barrier, an uncrossable gulf. But now we know the gulf has traffic. It has currents and flows.
Objects cross it, and if objects cross it naturally, perhaps intelligence can cross it intentionally. The existence of interstellar comets makes interstellar travel seem less impossible. If a rock can traverse the distance between stars, why not a spacecraft? Why not a probe? Why not eventually a civilization? This brings us back to 3i Atlas and the question that haunts this entire story. If we're being visited by natural objects regularly, might we also be visited by artificial ones? And if we are, would we recognize them? The framework for answering this question is SETI, the search for extraterrestrial intelligence. For decades, SETI has focused on detecting radio or optical signals from alien civilizations. The assumption has been that intelligence announces itself through communication. But what if intelligence travels instead of broadcasting? What if advanced civilizations don't sit in one place, shouting into the void, but instead send probes to explore, to gather data, to map the galaxy? If that's the case, then the search for extraterrestrial intelligence should focus not just on signals, but on objects. Every asteroid, every comet, every bit of cosmic debris becomes a potential candidate for investigation, and the bar for determining artificiality becomes critical. This is why the 3i Atlas case matters beyond its specific details. It's a test case for how we handle ambiguous objects. If we can't agree on what would constitute evidence of artificial origin, if our institutions suppress data, whenever something seems unusual, then we might be visited repeatedly and never recognize it. The implications extend to how we think about humanity's future as well. If we aspire to become an interstellar species ourselves, if we imagine sending missions to Alpha Centauri or Proxima Centauri or other nearby stars, then we need to understand how interstellar travel works in practice. A probe sent to another star would take decades or centuries to arrive, even at a significant fraction of light speed. It would need to survive the journey function upon arrival and ideally report back. Such a mission would require technologies we're only beginning to develop: compact energy sources, radiation shielding, autonomous navigation, perhaps even self-repair capabilities. But it's not science fiction, it's engineering. And if we're contemplating these missions, then civilizations older than us with centuries or millennia more development might already have solved these problems. Their probes might already be traveling, and one of them might have just passed through our solar system while we argued about data release schedules. The cosmic context of 3i Atlas is this: we live in a universe where interstellar exchange is real. Matter flows between stars, and with it flows information, chemistry, and potentially intentionality. How we respond to that reality, how we study these visitors, how we share what we learn, these decisions will shape not just our science, but our civilization's trajectory. Because if we're not alone, if the galaxy is populated by other minds, then making contact or missing contact becomes the most consequential event in human history, and we might not get many chances to get it right.
Let's be honest about what we know and what we don't. We know that 3i Atlas is an interstellar object. Its trajectory confirms it came from outside our solar system. That much is not in dispute. We know its chemistry is unusual. Carbon dioxide-dominated nickel-rich emissions, cyanide compounds. The specific details of this chemistry are still being analyzed, but the broad strokes are established. We know it displayed behavior that's hard to explain with conventional comet physics. The sunward jet, the non-gravitational accelerations, the structured halo. These observations exist. Multiple independent observers recorded them. We know that data from key observation windows is missing or delayed. Psyche's September observations, HiRise's October imaging, ESA's extended embargo. These are facts, not speculation. What we don't know is why. And that why has several layers. Why was 3i Atlas's chemistry so unusual? Is it because it formed in a very specific type of environment around a different kind of star, or because its composition was processed during millions of years in interstellar space, or because its surface has been altered by mechanisms we don't fully understand? The carbon dioxide dominance alone suggests formation conditions quite different from typical solar system comets. But different in what way?
What kind of protoplanetary disk creates CO2-rich ices as the primary component? We have theories, but theories need testing, and testing requires more data, more objects, more opportunities to study interstellar visitors and compare them. Why did the jets behave anomalously? Is it viewing angle? Is it unusual rotation? Is it explosive outbursts from subsurface pressure? Is it plasma effects we haven't accounted for, or is it something else entirely? Something that requires new physics or new assumptions. The sunward jet remains the most controversial observation. Natural explanations exist, as we've discussed, but are they sufficient? Do they fully account for what was seen, or are we stretching natural models to cover phenomena they weren't designed to explain? We don't know. We can't know without better data. And that's precisely the problem. Why are the data gaps so systematic? One missing observation window might be bad luck. Two might be coincidence. But the pattern we've seen, multiple spacecraft, multiple agencies, multiple instances of data that should exist but doesn't, that pattern demands explanation. Is it technical failures? Is it bureaucratic dysfunction amplified by the government shutdown? Is it scientific caution institutions holding data back until they're certain of their interpretations? Or is it something more deliberate, a coordinated effort to control information flow about an object deemed too sensitive for immediate public release? Each explanation has some support. Each has holes. And without transparency from the institutions involved, we're left guessing. Why has ESA embargoed data until April 2026? The official explanation is proprietary periods for instrument teams. But is that the whole story? Or is there something in the observations that requires extended review? Something that ESA scientists are still trying to understand or interpret? When April 2026 arrives, when the data is finally released, will it resolve the mysteries or deepen them? Will we see clear, high-resolution images of a normal comet nucleus? Or will we see something that raises new questions, something that makes the wait seem justified or perhaps even insufficient? Why did NASA not explain the missing Psyche observations? This is perhaps the simplest question with the most unsatisfying answer. Either the observations don't exist because the opportunity was missed, or they exist and have been withheld. A brief statement from NASA could clarify which scenario is correct, but no such statement has been made. The absence of explanation is itself anomalous. In the modern era of science, communication agencies typically over-communicate. They issue statements about routine operations, mission updates, technical glitches, everything. Silence is rare, and silence about a high-profile observation of an interstellar object is nearly unprecedented. What would high-resolution images of 3I Atlas's nucleus reveal? This is the question that haunts the entire investigation. We've seen distant images showing the coma, the jets, the overall behavior, but we haven't seen close-up views of the nucleus itself. A natural comet nucleus is irregular, pockmarked, shaped by billions of years of random collisions and gravitational interactions. It would show craters, fractured terrain, layered deposits. It would look geological, the product of natural processes. But what if close-up images showed something different? What if the surface had regularities, patterns, geometric features? What if the shape was too symmetric? What if structures were visible that couldn't be explained by natural erosion and impact history? We don't know what those images show because we haven't seen them. And that absence of information is driving speculation. What happens to data that's too anomalous to release? This is the question that extends beyond 3I Atlas. If a spacecraft captures an observation that genuinely suggests artificial origin, that shows clear evidence of technology, what protocol activates? Does the data flow immediately to the scientific community and the public? Or does it trigger national security reviews? Does it get classified? Does it disappear into governmental or military channels, analyzed in secret with decisions made far from public view? We don't have clear answers because the scenario has never been publicly acknowledged.
Space agencies don't have published protocols for what to do if we discover alien technology, at least not protocols that we, the public, are allowed to see, and that creates a logical bind. If such protocols exist and are classified, we wouldn't know about them until they were activated. And if they're activated, we might never know, because the whole point of classification is to keep information secret. Will the April 2026 data release actually happen? ESA has set a date. But dates can be extended. Embargoes can be expanded. Technical issues can delay releases. What seemed like a firm commitment in October 2025 might become further analysis required. By April 2026, we'll know only by waiting. And in the meantime, 3i Atlas continues to fade, receding from the sun, moving beyond the range of follow-up observations. The clock is ticking. Every month that passes, the opportunity to gather more data diminishes. By the time all the embargoed observations are finally released, it may be too late to use them to guide new observations. Why has the scientific community not pushed harder for transparency? This is perhaps the most troubling question. In previous cases where data access was restricted when embargoes seemed excessive, scientists have publicly complained. They've written letters, organized petitions, demanded explanations. With 3i Atlas, there's been remarkably little public pressure from the astronomical community. Some researchers have noted the data gaps in private conversations in online forums, in conference hallway discussions. But few have made formal complaints. Few have demanded answers publicly. Is it because they trust that normal processes will eventually release the data? Is it because they fear professional consequences for seeming too demanding? Is it because those who've seen preliminary data know something that tempers their concerns? Or is it simply exhaustion, a community too overwhelmed with other work to mount an effective advocacy campaign? We don't know. But the relative silence from the scientific community is itself noteworthy. What will we learn when more interstellar objects are detected? The next Oumuamua, the next 2i Borisov, the next 3i Atlas, they're coming. The Vera Rubin Observatory will find them. And each one is an opportunity to test hypotheses, to compare properties, to build a statistical sample. If all interstellar objects show unusual chemistry that tells us something about common formation processes in other systems, if some behave strangely and others don't, we can look for patterns that explain the differences. If we see a range of properties, we can begin to categorize and understand interstellar populations. But that work requires data. It requires transparency. It requires that when the next visitor arrives, we do better than we did with 3i Atlas. Finally, the most profound, unanswered question: are we alone? Not in the grand cosmic sense, not is there life in the universe, but in the immediate practical sense. Are we alone in this solar system right now? Is 3i Atlas the only visitor currently passing through? Or are there others, undetected, moving through the darkness beyond our observational reach? We've likely missed dozens or hundreds of interstellar objects that passed through the solar system in recent decades, simply because we weren't looking or didn't have capable enough detection systems. How many opportunities for discovery have we already squandered through ignorance rather than suppression? And going forward, as our detection improves, as our capabilities expand, what will we find? More comets and asteroids, or something else? Something that forces us to confront the reality that we're not alone, that intelligence has spread through the galaxy, and that the visitors we've been waiting for have already arrived. These questions remain open. Not because they're unanswerable, but because we've chosen not to pursue the answers with sufficient urgency and transparency. The tools exist, the methods exist. What's missing is will. The will to look carefully, to share openly, to accept whatever we find, even if it challenges everything we thought we knew. 3i Atlas came and went, its leaving now fading into the cosmic dark, carrying its secrets beyond the reach of our instruments. We had a moment to study it. We used some of that moment well and squandered some of it. We learned things, but we missed opportunities. The object is gone.
but the questions remain. And they'll remain unanswered until we decide that transparency matters more than institutional caution, that discovery matters more than control, and that humanity's right to know about its cosmic context outweighs any bureaucratic impulse to manage information. Until then, we're left with fragments, pieces of a puzzle that might form a picture of profound importance, or might simply be a comet with unusual properties. We can't know because we don't have all the pieces, and we might never get them. So here we are at the end of this investigation, and we're left with more questions than answers, which is perhaps appropriate. The universe is under no obligation to provide us with tidy conclusions. 3I Atlas arrived in July 2025, a visitor from interstellar space, carrying with it the chemistry of another star system. For a few months it was close enough to study, close enough to photograph, close enough that our best instruments could analyze its composition and behavior. It was an opportunity, rare, fleeting, irreplaceable, and we fumbled it, not completely. We learned things. The spectroscopy revealed unusual chemistry. The images showed anomalous jets. The trajectory tracking documented strange accelerations. These are real data, real contributions to science. But we could have learned so much more if the Psyche observations had been released, if the high-rise images had been shared, if the ESA data hadn't been embargoed for months, if the government shutdown hadn't paralyzed NASA during the critical observation period. If the story of 3I Atlas is not really about a comet, it's about us, about how we handle discovery, about the gap between what we observe and what we share, about the tension between scientific transparency and institutional control. It's about what happens when something doesn't fit our models, when observations challenge expectations, when the universe presents us with an anomaly that we can't easily explain. Do we lean into the mystery? Do we embrace the unknown, or do we retreat into caution, suppressing data until we can massage it into comfortable narratives? The evidence suggests we do the latter. Not maliciously, not conspiracies in smoke-filled rooms, but through bureaucratic inertia, through institutional self-protection, through algorithms that filter out anomalies, through embargoes that seem reasonable in isolation but cumulative create opacity. The result is a system where the most important discoveries, the observations that might genuinely change our understanding, are the least likely to reach us quickly, or perhaps at all. Science thrives on transparency. That's not an idealistic slogan. It's a functional requirement. Science advances when observations are shared, when multiple researchers examine the same data, when hypotheses are tested against independent verification. Remove transparency, and you remove the engine of discovery. The handling of 3I Atlas suggests that transparency is more fragile than we realized, that when the stakes get high enough, when observations become uncomfortable enough, institutions will sacrifice openness to maintain control. And that should concern us, not just as space enthusiasts or scientists, but as citizens of a world that's beginning to reach beyond itself. Because if we can't handle transparency about a comet, how will we handle more consequential discoveries? What happens when we detect biosignatures in an exoplanet's atmosphere? When we find unambiguous evidence of past or present life on Mars? When we receive a signal from another civilization? When we encounter something in space that's clearly artificial, clearly technological, clearly from an intelligence not our own? Will those discoveries be shared immediately, becoming moments of collective human experience? Or will they be gate-kept, classified, released only when someone decides we're ready? The 3I Atlas case doesn't answer those questions, but it shows us the framework within which they'll be decided. And that framework is troubling, yet there's hope in awareness. The very fact that we can see these patterns, that we can map the data gaps and question the delays, means we're not powerless. Transparency requires demand. If the scientific community and the public insist on openness, institutions will have to respond. The next interstellar visitor will come, sooner than we might expect. The Vera Rubin Observatory is online. Detection capabilities are improving. Within a few years, we'll have another Oumuamua, another opportunity to study a messenger from the stars. When that happens, we can do better. We can demand that data flows freely. We can insist that observation schedules are met and honored. We can refuse to accept technical difficulties or extended analysis periods without detailed explanation. We can choose transparency over control. The alternative is to drift toward a future where space science becomes like every other domain of modern life, stratified into those who know and those who are told what they need to know, where discoveries are managed, narratives are crafted, and truth is something that's released on a schedule determined by institutions rather than data. That future is not inevitable, but it's where we're heading if we don't change course. 3i Atlas is gone now. It's speeding outward beyond Neptune's orbit, beyond the reach of our telescopes, heading back into the interstellar dark. It will travel for millennia, perhaps encountering other star systems, perhaps passing unnoticed through empty space until the universe itself grows cold. We had our moment with it, a few months, a brief encounter, and we learned something not just about the comet but about ourselves. We learned that we're not as ready as we thought we were, not ready for anomalies that challenge our models, not ready for institutional transparency when discoveries get uncomfortable, not ready to confront the implications of living in a universe that might be far stranger, far more populated, far more mysterious than our textbooks acknowledge. But perhaps that's okay. Perhaps recognizing our unreadiness is the first step toward becoming ready. Perhaps the fumbled observations, the missing data, the uncomfortable questions surrounding 3i Atlas will teach us something valuable about how to handle the next visitor. Perhaps the universe will keep sending us messages. Some will be comets and asteroids, cosmic debris from other systems. Some might be something else, something we're not expecting, something that forces us to reconsider our place in the cosmos. When those messages arrive, when the next interstellar visitor crosses our detection threshold, we'll face a choice. Do we look away? Do we filter the data through institutions that decide what we're allowed to see? Do we accept gatekeeping as the price of avoiding uncomfortable truths? Or do we insist on seeing clearly? Do we demand that the data, all of it, flows to those who wish to examine it? Do we embrace transparency even when the observations challenge us, even when they don't fit, even when they force us to admit that our understanding is incomplete? That choice is not hypothetical. It's happening now. Every time an observation is delayed, every time data is embargoed, every time an anomaly is filtered out by algorithms or suppressed by caution, we're making that choice. We're choosing what kind of civilization we want to be. One that faces the universe honestly, or one that prefers comfortable illusions. 3i Atlas has shown us the stakes. It's revealed the mechanisms by which information is controlled. It's exposed the gap between what is seen and what is shared. Now the question is, what will we do with that knowledge? Will we demand better? Will we insist on transparency? Will we refuse to accept data suppression no matter how it's justified? Or will we shrug and move on, accepting that some things are too important to be left to the public, that institutions know best, that we should be grateful for whatever crumbs of information we're given? I can't answer that question for you. But I can leave you with one final thought. One question to carry with you as you drift towards sleep, as you contemplate the vast darkness beyond our world, as you wonder what else is out there moving through the night, perhaps watching us as we watch the stars. When the next interstellar visitor arrives, and it will arrive perhaps sooner than we think, will we be ready, not just to observe it, but to see it for what it truly is? Or will we once again allow the most important data to slip through our fingers, hidden behind closed doors and missing windows, leaving us to wonder what truths we were too cautious, too controlled, or perhaps too afraid to confront? The universe is waiting. The answer is up to us.